Yeah, it might have timed out and you need to start again. And I need to start again. It'll take a minute or so. So what we'll do is we'll continue on with the MDM2 example that Charles showed you. And we'll do the molecular replacement for that case. Okay. So I've had to restart my Dexter's Cloud session, so I need to restart CCP4 Cloud. So I'm going to go to the terminal again. And I'm going to run CCP4 Cloud remote. Like that. Like we did before, and that's going to open up the cloud again. I think that's where we left off before lunch. So this example you can do yourselves if you want. You can do it later. But it's very similar to the MDM2 case, so we'll do the MDM2 case and follow that. So I will close this tutorial. And then I will log back in CCP4 Cloud. Brings me to this view again. So I'm going to go back to the MDM2 tutorial that we started this morning. So from the project list, click on the MDM2 tutorial. And you should see something like this. Can everyone see that? Everyone's at that point? Okay, just going to get my glasses. So we go back to where we did aimless. So you should all have an aimless task. Like that. Has everyone got aimless? Anybody not got that? No? Okay. So that's the point at which we produced a merged MTZ file that we can use for molecular replacement. And it's in P6122, but at this point it could also be P6522, it could be the enantiomer. We won't be able to tell until we do molecular replacement. But Phaser will allow us to check both possibilities. And the resolution is about 1.55 angstrom, so it's quite high resolution. And statistics all look good. CC1/2 is very high. So let's from this point then add a new task. And the task we're going to add will be the definition of the asymmetric unit context. So we're going to try and figure out how many copies of the molecule are we searching for. And this is that task here. If you don't see it, you can go to A to Z and you can search for asymmetric, and it will come up with the same task. So we click on that, and that brings up the task window for us. And it automatically loads the reflection data, from which it's going to take the unit cell volume information, and also the sequence, which it will use to calculate the molecular weight. And with those two bits of information, we'll be able to figure out how many copies there are in the asymmetric unit of this particular sequence. So we can leave everything else the same. It'll use this AI predicted method to figure out the contents, and we just click run. And it shouldn't take too long to run. And it will produce some tables for us. Okay, the first thing we see is that it's telling us the AI predicted method has predicted a solvent content of about 58%. So the rest of it should be molecular content. And if we scroll down a little bit, we have a results section. And this tells us that there is one copy of the molecule in the asymmetric unit with an actual solvent content of 64%. So the AI predicted 58, and the nearest solvent content that has a whole copy of the molecule is 64%. So the actual solvent is 64%. So it's close enough that it gets it right. So it takes out one copy, and with a probability of 88%. So it's pretty confident that there's one. There's a much lower probability that there are two copies with a much lower solvent content, but that's less likely. It's less likely to have 29%. So we can be pretty sure there's most likely one. But we should always consider this as an estimate. It's not an actual guaranteed value. You always have to just take it that this is the best guess, and you may have to explore other possibilities. But in this case, it's most likely one. Okay. So the next step to do then is to do the prediction of the structure. So again, I'll click the green cross to add a new task, and then in here I'll look for structure prediction. And it should give you this option here. So this task here is the structure prediction task, and that will run Colabfold underneath, which is very like AlphaFold. Okay, so I click that, and that loads up this window, and in here it's taking the sequence for our target, and we're going to predict the actual structure from that sequence. A couple of other things. So if we were dealing with a complex, if we had a dimer or a trimer or a tetramer that was predicted to be in the asymmetric unit, we could say, give me 2 or give me 4 or whatever. But in this case, we think there's only one copy, so we predict 1. And then the number of predictions. So AlphaFold usually gives you about 5 predictions, but often they're very similar to each other. So for the purpose of molecular replacement, all of them will do. So we don't need to predict 5, we just predict 1. And we'll use that for molecular replacement. So just click run then. And that will go off, and it shouldn't take too long, but because we're all doing it, some of your jobs might get queued up like my one. We'll give it a minute. And underneath, that will do the prediction. While we're waiting, does anyone have any questions?
This running new prediction or just creating from the database compared with something?
In this case, it's doing a new prediction. Although we do cache predictions. So it should pick up from the cache, but it's sitting in the queue waiting. Has anyone started prediction? Or are you all queuing at the moment? Can anyone yet see the model? No. Did you get past that stage? You have no sequence in your project. Okay. Yeah, you need to import the sequence. So, from this class here, this one will average one. And go all tasks. Take import. Import from cloud. Select file. And then sort directory. Pick the sequence file. Select it. Apply. Finish. Then you can only a selection from the task sequence. Now
Yeah, this seems to be happening everywhere.
all right.
There's no way to look
Yeah, so it seems that some people didn't import the sequence file when we imported it.
even though they didn't contact they didn't start not so from the report part.
Yeah,
Then the task cannot see
yeah, that should be in the same branch. It won't, if it's in a different branch, it won't see it.
so you cannot modify the result.
Well, you can press Control and highlight where you imported that sequence, and then you can use it. So if you control and highlight the two, the job you want to add to.
Select studio some click
Yeah, but that will work. Okay, so my one has finished. How is everybody else doing? You have your prediction. You have yours. Slowly working through. So while we're waiting on everybody to finish, I'll just explain what this shows you. So we're given a few different plots in the output. And the first one we see here is called the the PAE matrix, which is the predicted alignment error matrix. And if I expand that, I'll open it in a new open image, a new tab. So what this shows is, so this is a fancy matrix plot that comes from AlphaFold. And what it shows essentially is if you could align the predicted model to the actual structure, the theoretical actual structure, this would show you how well aligned each residue would be to the true residue position. And blue scores mean low alignment error. So that means that the alignment is good, predicted alignment is good, and red is high. So what we see here is that most of the predicted alignment error is low. So overall the model quality prediction is good. But there is a region here in red where at one of the terminals that has a high error. So we need to have a look at that. But that's what that tells you. And this can be useful sometimes because it can show you where there are likely to be domains within a prediction. So what you see if you've got like two domains usually is you'll see two blocks of blue surrounded by red, where the blue corresponds to the alignment within a domain, but those domains don't align well with, those residues in each domain won't align well with the other residues in the other domain. But in this case it's fairly straightforward, it's pretty clear, single domain, a low error in the prediction. And then the other plots we see are, this is essentially the PLDDT score, so the confidence score. Let me expand that. There we go. So this one is PLDDT score. So we see values of close to 100 for most of the structure, meaning that AlphaFold is quite confident in all of those residues. Apart from here at the end terminal where the PLDDT values drop. So that means that there's low confidence in this region. And if you scroll down a bit more, this plot shows you, so when AlphaFold makes its prediction, it does a sequence-based search of all of the sequence database to identify similar sequences. And if it finds a lot of sequences aligning to parts of the structure, then that aids the prediction. So that's what we see here. We've got a lot of sequence hits in the sequence search, so we've got a pretty high quality prediction. But then further down we can look at the model in 3D by clicking on this UGLIMAL viewer. So if I click on UGLIMAL, it will bring up this 3D viewer, which is just a viewer, molecular graphics viewer. And what you can do in here is if you press the H key, H for help, it gives you the list of options that you can use. And one of them is the coloring of the model. So if I press C for coloring, I can change the color to the PLDDT coloring from AlphaFold. And there we can see the confident regions and the less confident regions. So the blue, this blue area is the high confidence residues, and then down here in this end terminal we have some orange and yellow residues which are the low confidence residues. I'll just get rid of that help so there we can see it. So for molecular replacement, we want to get rid of this part. So before we do phaser, we need to remove these residues, because AlphaFold doesn't think they're accurate. The chances are it's not going to be like that in the crystal. And if we leave them in, what might happen is when phaser places the model, those residues may overlap with a symmetry made. And that would cause what's called a clash. And if the clash is too big, phaser will reject that placement. So it may reject the correct placement of the model because of those residues. So we have to get rid of them. So what we'll do is we'll run the preparation task. So how many of you are still waiting for AlphaFold to finish? Any of them? Has it finished for everybody? Nobody's waiting. Okay, good. So we can follow the prediction task with a new job. So I can click the green cross again. And what happens is I want to run a program called slice and dice. So I type slice in here, and it gives me two options. So the first one here, MR with model splitting. That will prepare the model, but it will also put the model into molecular replacement and run it all automatically for you. And you can do that if you want, but we want to do it step by step. So we'll just choose this second option, which just does the model preparation step, which is three things. It will truncate those low confidence residues. It will convert the PLDDT values into p-factor estimates for phaser. And if we needed it to, we could get it to split the model into domains. But in this case, from that PAE plot, we saw there's just one big blue block, so there's probably only one domain. And you can see that in the model, there's a single domain. So we're going to just run that task. And it's picked up the AlphaFold prediction from job number 7. And it's detected that it's an AlphaFold model, so it'll convert the PLDDTs into p-factor estimates. And then here, if we wanted it to split it into domains, we could make this number greater than 1, but we're going to keep it as a single globular domain, so we leave that value as 1. And this is the threshold at which it's going to remove those low confidence orange residues. So the PLDDT value of 70. So that will just keep the blue parts for us. So I click run on there. And that will start that preparation. And it runs very quickly. And what we get, if we look, we can look in ugly model again at what it's produced. And now we can see that it's just kept the globular part and it's removed that N-terminal part that we had before. So this is our molecular replacement model that we give to phaser. Okay. So let's run phaser now. So we add a new job. And I'll just again search for phaser. We could use MOREF as well, but we'll use phaser. And it's molecular replacement with phaser. That's the task we want. So I click on that. And that brings up the phaser interface. Okay. So it's loaded our structure revision, which essentially is our reflection data. So this is the reflection data at this point, plus the sequence. It's going to try all compatible space groups. So if you remember when Charles showed you the pointless output, it was ambiguous. There was P6122 and P6522, so the enantiomorphs. So it can be either one of those two. We don't know until we run molecular replacement. But Phaser will allow us to check both of them. So if we just say all compatible space groups, it will check both of those options for us. And then this is where it's picked up the model that we made using the slice and dice process. And by default, it's going to look for one copy in the asymmetric unit. And assuming a similarity to the target of 1 angstrom. Now this is something that Phaser uses to gauge the error in the model. So in the old days when we used homologous structures, we used to tell Phaser the sequence identity of the homologue to the target. But now with AlphaFold models, we don't have that value. But a good value just to give as a rule of thumb is about 1 angstrom RMS difference between our model and the true structure. And that tells Phaser the error estimate. And Phaser will use that inside itself to help the positioning of the model. So normally, if you're using a predictive model, you don't have to change that value at all. Okay, so let's click run and set Phaser run. All right. So Phaser does a few steps inside itself. It does a bit of analysis of the data, it works out the anisotropic distribution of the data, and various other bits of information that it needs for doing molecular replacement. And then the key steps involved are the rotation search first, where it rotates the model against the data to find the best rotation for the model. And once it identifies the best or several best rotations, it will then do a translation search, so it will move the model in 3 dimensions within the unit cell to find the optimal position. And once it finds that best position, it will do a little bit of rigid body refinement to better place the model around that position. What we find, give it a second. It should give us a final log likelihood gain and TXZ score. If you remember, I talked about those two scores. Let me close this and reopen it. There we go. Okay. So the first thing we can see now that it's finished, that it's actually changed the space group. So it's found that P6522 is actually the correct space group. That's the first thing to know. And then we can look in detail at what the output is. So if we look at these plots and we go to the final plot, so here's the rotation function, the translation function, and then it's done 3 rounds of rigid body refinement, and in each one it's increased the resolution that it's using to do that refinement. So if we look at the last one here, refinement after placing component 1, we can see what the scores are like. So I click the little arrow and it gives me these 2 options here. And the first one is our log likelihood gain score. And we can see that we have a single placement for the model that scores much better than every other possible placement for it. And that score, the log likelihood score, is 640. If you remember what I said a value better than 60 is good. And here we have 640, so this is a really good solution. We can also see, if we scroll up, and you click on this MR result section, you can see a snippet from the log of Phaser, which is basically the solution line. And what this shows is this line here is the actual rotational translation it's applied to the model to place it correctly. So the Euler angles and then the fractional movement across the unit cell. And our TFZ value for the placement is 29.5. And I set a value better than 8, and we've got 29. So this is clearly a solution, both from the LLG score and the TFZ score. And we could even have a look. So what I'll do is I'll actually have a look at the solution in Qt. Now you may not be able to open Qt, but we can try. So I'll add a job and I'll find Qt in this list. So there's Qt, model building with Qt. Now don't worry if you can't run it, because if you've logged in directly on the web page, you may not have access to Qt. But if you're in Dexter's Cloud, you will. And it might be a bit slow, so let's try it. Right, I only want to look at the packing here. So let's cancel everything. We're not interested in anything to do with model building at the moment, or saving the file. So we just click OK and cancel to anything that appears. And we'll bring up the main window from Qt. I'll expand it. So that's our solution. And if I zoom in a bit, we can see the density, and we can already see, even though this is come straight from Phaser, we can see there's some difference mapped here. Green density meaning there's something missing from the model that needs to be built. But we won't do any model building. You never do any model building straight from molecular placement. You have to do some refinement first. But what I'm interested in here is just to look at the crystal packing to see if it makes sense. So I'm actually going to turn the map off. So I'll go to Display Manager, and I'll just undisplay the electron density and just show the model. And I'm actually going to just change it to C alpha representation. So we just see the C alpha positions. Okay? So that's from Display Manager. And I've turned off the density and changed the map, the model to C alpha. Okay. And then I'm going to zoom out a little bit. And I'm going to turn on the symmetry base on the unit cell. So if I go to Draw, and I click on Cell and Symmetry, so that's Draw, Cell and Symmetry, I can show the symmetry base. So I click on Draw, Cell and Symmetry, and in here, I turn Symmetry on, and I select the Symmetry by Molecule option here. So there's a button you can press, Symmetry by Molecule. And that brings up this window. And in here I can change how I represent the models, the symmetry models. So I want them represented as C alpha as well. So I click on the C alpha button here. So any symmetry copies will be shown as just C alpha. And I click OK. Alright. then I want to see more copies of the symmetry. So I'm going to change the symmetry radius to be something like, let's say 40, make it a bit bigger. And I'll also tick this box to show the unit cell. And that shows me the unit cell. And if I click OK, we can see our molecule and all of its symmetry bits. In fact, I'll make it, that's probably good. So what we want to see here when we come from molecular replacement is we want to see a sensible crystal lattice. We want to see all of our symmetry baits in contact with each other so that they form a proper scaffold. If we had big gaps in between copies, that would mean we probably haven't found everything that we're looking for, and it's not a correct solution yet. In this case, we have quite big gaps here where large solvent channels, which is okay because we have our molecules making a ring around those solvent channels and they're all touching each other. So that makes sense. The other thing we're looking for is that there's not overlaps between the molecule and the symmetry maze. So it's not overlapping with each other. And that's not happening either. We see that there's clearly no clashing going on. So that's a good thing to look at immediately coming from molecular replacement. Does your crystal lattice make sense? Have you found everything? And there's no clashing. So, and in this case, that looks to be right. So that's all good. So I can close Coop now. I can find the close. So I'll exit Coop. I'll do is I'll do some jelly body refinement with the solution from Phaser. So I click back to the Phaser job, highlight the Phaser job, and then I can add a new task to that. And this time I'm going to look for Refman. So this middle one here with the diamond. I'm going to run that, and it's loaded up the solution from Phaser. And what I'll do is by default the number of cycles it's going to do is 10, but we need to do more. So I usually say do 100, but in the interest of time I'm going to do 50. This case. And then this jelly body option I talked about, which is under restraints, I will turn that one on. So I click yes. So there we have it. We set the number of cycles to 50, and then under the restraints menu we turn on use jelly body restraints. Okay? So you usually only do this after molecular replacement once. When you've done it once and you've done many cycles, any refinement you do afterwards, you turn this jelly body off and you do normal restraint refinement where you're refining against experimental data and chemical knowledge, using those two things to refine them. And Keitaro is going to talk a lot more about refinement and will explain more. But for now, we'll just do this jelly body option. And we'll click run. And what we should see is our R factors, which are the measure of the similarity between the model and the data, will start to drop. And they're dropping quite quickly in this case. So they started out at close to 0.5, and now they're dropping all the way down to 0.4. Each cycle they're getting better and better, which means our model is improving. And while the model improves, that also improves the phases that we get, which subsequently improves the map. So we're all the time improving our phases and then improving the electron density map. And you can see that they've sort of stabilized now at around, they're still in the high 30s, so there's, well, for this kind of resolution, 1.5 angstroms, when the model is complete, we'd probably expect to get about 0.2, an R factor of about 0.2, maybe in the middle R probably about 0.1716, and an R free of about 0.2, 0.21 or 0.22. So there's still some work to do, but there's probably bits of the model to build. And at this resolution, there'll be all sorts of stuff in the solid, like waters and things like that, to build as well. But at this point, we can see that our molecular replacement has worked and our model is starting to refine. Oh, the other thing with this one is there's a ligand in here, which we'll show you how to build later. Okay, so let's have a look at what it looks like in UGLIMO. So we click on the UGLIMO link. And this will load up our density as well. There we go. And in here, again, I'll press H for the help key. And then you can see these square bracket keys can be used to expand the map radius. So that's what it is on a UK keyboard, and hopefully it's the same for you, but there'll be some keys that, sometimes the keys are a bit different. But normally it's the square bracket keys. So if I press the square bracket, we can expand the radius of density that we see. I'll turn H off. There we see, we can see on that, we can actually see a ligand here. If I zoom in a little bit. I press the N key to zoom in. N for macromolecular. You can just about see the ligand here. So there are things to be finished in the model, but overall it's looking good. Lots of good fit to the map for the model that we have already, and clear evidence that there are things to be built. Okay, so close that. What we'll do is we'll do one more step. So in scenarios like this where there's still parts of the model to be built, a good thing to do is to run a program called ModelCraft, which is an automatic model building program. And that will complete parts of the protein that haven't been built yet for us automatically. So we won't have to do it by hand. We can run that if we add it here. We can look for a program called ModelCraft. Like that. You find this program, automatic model building with ModelCraft, Puppeteer and Nautilus. And what this does is it tries to build into the electron density, and it does several cycles. So it will build into the density, it will refine the model, and then it will do it all again with the improved density, so that we end up with a more complete structure. So I'll just start that job. And you don't change anything, it will load up the density of the model for us automatically. And we just click run. And that will go off, and that might take 20 minutes or something, but it will give us a near complete model at the end with a little bit of work to do to fit the ligands and a few other bits at the end. But I'll stop at that point and I'll hand over to Keitaro to tell you more about the refinement. I'll close that. And he will show you how to build the ligand as well. That's right. Yeah. Okay. So what are you doing on your lab?
For my presentation.
Okay. I can share this project with you. I'm going to share the project with Keitaro so you know from his laptop. I might have to be you, Charles, to be on the project.
Would I have to share it?
Yeah, you, I think I can share it. Does anyone have any questions, actually? Anything about any of that stuff? Any questions?
Can I start? So, by the way, it's not cold for you. Actually, it's cold to me, but it's cold.
Yes, very cold.
Could we increase the temperature? Oh, yeah, it's good to know. Not just me. So, in this session, I'm going to cover mostly refinement, the program called RefMatChat, and also some bits about PDB redo. So as we have seen, X-ray crystallographic structure analysis started with data processing and then we did phasing. So today we did modular replacement phasing because nowadays it's mostly sufficient. So after modular replacement, we obtained a model and model placed in our crystal coordinate frame and density map. Now we need to start improving the structure, and only after that we can deposit the model to PDB and discuss the structure and publish the paper. So, as you may already know, structural refinement, the model improvement process is an iterative procedure. And there are several refinement programs, including RefMap 5 or Cybercat is mine, within CCP4 and outside CCP4, Phoenix Refine or CNS or Bastard. These refinement programs do refinement calculation, that is optimization of atomic model parameters against the observed data. The observed data are what we got in the data processing stage, that are intensities, structural intensities or structure factor amplitudes derived from intensity. The thing is that in crystallography, the data, observed data are in reciprocal space, and we need to use those data for this refinement calculation. Because as Ronan mentioned, map is important, but it's being updated every time model is updated. So in this refinement calculation, we always use data from data processing. And after that, we check the model. This is a validation step. Mostly from morphology that evaluates the geometric quality, and we also have to check data model agreement. And then we have to start code to do iterative, interactive real space refinement. We inspect the model with the density, and most likely we find some new errors, and then we correct it. And after that, we again optimize the model using refinement programs. So we repeat this process until no improvements can be made. So again, this is what refinement programs do, but let's look into a bit detail of this. So, as I said, refinement is optimization calculation of atomic model parameters. So, what are atomic model parameters? Obviously, they include the coordinates, the atomic coordinates, x, y, z coordinates of each atom. But also, it's important to refine ADPs, atomic displacement parameters, so-called D factors for each atom. I will explain this in the next slide. The programs try to maximize the posterior probability, that is, probability of the model given data. To do this, we have to maximize the product of this probability called likelihood and this probability of the model. This is about the prior knowledge. So, yeah, because of this, we often say we do maximum likelihood refinement for macromodular crystallography. So this is a target function that will be minimized in the refinement programs. So there are data terms. This is a minus log of likelihood, and the other term is restraint. This is minus log of T model called restraint. And there is a important parameter weight. This is also what we can give in the CCP4 cloud interface in the RefMap. So you may remember this. You may need to remember this for the next stage. So what are ADPs and occupancies? So it's important to remember that we are seeing averaged structures in crystallography and also in single particle analysis using cryogenics. So, because in the crystal there are many protein molecules, and we need some finite time to collect data. So the structures are averaged during, yes, let's say data collection, not just temporal manner, also spatial manner. So if atoms moved during data collection, or they have slightly different positions in across the crystals, after averaging, we see kind of spread density. If atoms don't move at all, then we will see very sharp electron density for each other. So B factors or IDPs are to model these fluctuations. So there are two ADP models, isotropic and anisotropic. Isotropic ADPs is it just needs one parameter and no direction dependent. Anisotropic ADP is a directional fluctuation, but it needs more parameters, so it can be refined only at high resolutions. And in this figure, I'm showing how densities would look like for different B values. So please just look at blue curves. If B factor is 10, you see this sharp density, but for 20, then density got large. Not just height is smaller, but also the width became larger. For 30, it will be much broader. So this is how B factors affect electron density profile for each atom. And for occupancies, so occupancy is just at a scale. And the most typical use of occupancy is to model alternative conformations. In this example, we can see two distinct conformations of serine residue. So density itself doesn't look like serine, but this is actually serine with two different conformations. And we can assign occupancies to represent the fractions of these conformations. So in this case, occupancy is about 0.4 and 0.6 for this conformation and for this conformation. So it's important to note that it's hard to refine both occupancies and ADPs at typical resolutions. Because please look at this red curve. This is the atomic profile with occupancy of 0.5, 50% occupancy, with B values of 10. And compare this red curve with this blue curve. This is full occupancy, so the occupancy of 1.0 with B values of 20. They are quite similar, not exactly the same, but it's hard to tell the difference at typical resolutions. So this is why it's difficult to refine both parameters. So here I'm trying to introduce RefMat5 refinement, macromolecular refinement program in CCP4. Has been developed by Garrick for more than 20 years, and it supports various data sources, not just X-rays, but can also do refinement for neutron diffraction and electron diffractions, also called micro-ED or 3D ED, and also supports various data types. For example, in crystallography, of course, we can use structure factor amplitudes. And nowadays, these two options wouldn't be used, but if you do experimental phasing, you can use such information in the refinement. And in case of twinning, I think Charles will explain twinning later. In that case, we can also use diffraction intensity directly in the form of amplitude squared. It can also do structure requirement for single particle analysis inquiry, but it's not the topic today. Okay, this is about prior knowledge for the refinement. So, at typical resolutions in macromolecular crystallography, we have to use knowledge from small molecules. Otherwise, models wouldn't get have chemical sense. So, we use ideal distances of bonds, and also bond angles, and planarities, and chiralities, and some torsion angles. And in the refinement, we also use anti-bumping restraints for non-bonded atom pairs. And these ideal values all come from small molecule structures. And for the known components, like amino acids or some nucleotides and known ligands, for all these known components, ideal values are, and their sigmas, uncertainties are available from CCP4 monomer library. If you have installed CCP4, then you can access to this directory, or this library also publicly available from GitHub. These ideal values are all calculated using ASTRAC program, which is also available from CCP4. So if you have any new ligands or any ligands not available from monomer library, you can use ASTRAC to generate these ideal values. And these ideal values are used in the least square form. So in the refinement, for example, it takes the bond length in your model and compare it with ideal values, and take difference squared and divide by sigma squared. And these terms are summed up. So yes, the program tries to keep the ideal values as much as it can. So I just introduced quite basic restraints that are almost always used in macromolecular refinement. But at lower resolution, like 3 angstrom or less, we need some additional information to stabilize the refinement. So, for example, we may want to set up secondary structure restraints to, for example, to keep alpha helix. So to do this, we can set up the bond length restraints for the hydrogen bonds. Or if you have any high resolution homologous structures from PDB, or nowadays you can use highly accurate predictions from AlphaFold2, then you can use such reliable structures to set up external restraints. In this case, we do this thing. So you see many thin lines connecting non-bonded atoms, right? So the programs try to make these distances similar to those in the reference model. And these restraints can be set up using a ProSmart program within CCP4. But we don't want to make our structure completely the same or similar to the reference structure. So the program should allow some deviation from this reference model. So to do that, it uses some special restraining function, not like this quadratic form. This will try to make our confirmation completely the same as reference model. So this is not what we want. So rather we use these robust estimator type functions that that actually behaves quadratically when the deviation is small. This x-axis is the deviation, the difference of distances between our model and the reference structure. But if the deviation is large, it becomes Plato or not as strong as least square type function. So it means if deviation is large, it automatically allows such large deviations. So that if conformation is intrinsically different, it should be different. And derivative restraints. This was already explained by Ronan. I would like to just repeat it. So this derivative restraints looks very similar to what I explained before, external restraints, but this is a kind of external restraint without external structure. So these interatomic distances are kept, or the program tries to keep these interatomic distances over the refinement cycles. So this dramatically stabilizes the refinement, particularly after the molecular replacement. So, so today we just did very easy molecular replacement case, but when molecular replacement is hard, so for example, the model is not very similar to our structure, then even if molecular replacement worked, the score will be bad, and because the model is not very similar to our real structure, for example, R factor will be quite high, like more than 50%. Also, even in that case, jelly body refinement can make model better. And after, for example, 100 cycles of jelly body refinement, you may get R factor around 40%, and maps will be interpretable. Of course, it won't happen when the molecular replacement itself was unsuccessful. But yeah, it was trying. And here, when this derivative restraints is used, we should turn off the external restraints from cross-mark. Here I also want to introduce a new program, SabraChat. This is what I'm developing. It's meant to be a replacement for RefMark 5. And it actually started as a pipeline that internally used RefMark 5 for cryo single particle analysis. So if you, in case you have heard of SabraChat, you may think, oh, this is actually RefMark and it's only for cryo-EM. But it's not true anymore. It can do crystallographic refinement with its own refinement engine, independent of RefMark. And it's open source and also available from CCP4. I mean CCP4i2 or as command line, not yet from CCP4 Cloud. So again, SabraChat meant to be a replacement, but and it's slowly happening. But there was an urgent need to fix some problems in RefMark 5. So particularly in the reading and writing MMC files. So we made some a kind of evolutionary intermediate between RefMark 5 and SabraChat, and this is called RefMarChat. In this RefMarChat scheme, still RefMark 5 is used as a refinement engine, but model file reading and link identification, hydrogen generation, and restraint generations, all these things happen in SabraChat framework that actually internally use KME library. And it's also, Cyberchat also has responsibility in writing proper MMC file and also PDB file. So this has solved some problems in RefMark 5 and in 64i2 and cloud. This is used as RefMark 5 program. But I think you remember that you have seen RefMark chat in cloud. You used it already. So yeah, what's the benefit of RefMark chat? So it has enabled faster processing in the reading of model file and restraint generation part. And now you can feed compressed file, and it also writes an extended PDB file to overcome some limitations in the PDB. This is sometimes useful when code contains MMC file input. And also some new features of monomer libraries are only supported in this scheme. And more complicated situations about alternative locations, alternative conformations are supported, including microheterogeneity, that is different residue name at the same sequence position. Or this type of thing. This is a partial cleavage. So this one ortholog is connected to the previous residue, but the other one is cleaved. So it became terminal. So this is also possible in this scheme. And for neutron crystallography, this the use of RefMark chat is essential to properly handle deuterium fraction parameters that are introduced in RefMark just recently. Okay, I suppose you already know these things, but let's just review these how we assess crystallographic structures. So of course we should look at data model agreement. For this, we typically use R factors calculated in this way. We compare observed structure factor amplitude with calculated structure factor amplitude. Of course, some scaling included in the same curve. And we use cross-validation. So R3 and R1 are calculated, and R3 is for the subset of reflections not used for the refinement, and R1 is for the rest that are the reflections used in the refinement. So because R3 is from the reflections not used for refinement, should be larger than R1, but the difference should not be large. If the difference is very large, it may indicate some overfitting. And we have to check the chemical quality. For example, in the table, in the crystallographic table in publication, we always report bond lengths and angles, RMST values, and some more probability scores. But also we have to make sure that we didn't make any mistake in chiralities and planarities, and we shouldn't have severe crashes. And we also check using more probabilities and conformational preferences. So we compare side chain conformations, that is called rotamers, and or main chain conformations that are analyzed in the Chandra plot. And of course, the most importantly, we have to check density fit using Coot. So I know you will be very much worried about outliers reported by more probability, but I would like to stress that these outliers are quite useful stuff to find the model errors. So for example, in this panel, I used Coot Rotamer analysis function and found Rotamer outlier here. And if I go to these residues, this doesn't look very wrong, but it actually can be improved. So if we do this, then it fits to the density better, and it's no longer outlier. So this was good. And here I found Ramachandran outlier. It's here, and it's not very well fitted to the density, and attempted improvement, and it fitted to density better, and now it's not Ramachandran outlier. So these are good cases where outliers are quite useful to find what there are errors. Of course, it's difficult to judge at lower resolution. And again, I'd like to stress that outliers are not always wrong. So in this case, this residue is flagged as an outlier, Ramachandran outlier. But if you look at this structure, look at this residue, this is perfectly fitted to the density. And it's actually, you can actually find special interaction from other residue. So we can see this slightly favorable conformation is being stabilized by this interaction. So outliers can be interesting observations. So I know, sometimes I see people who think all outliers should be fixed. So we shouldn't have outliers at all, but this is not right. We should check density and try to fix it if it's wrong. Okay. And this is a kind of warning. So if you only worry about outliers, you may end up this type of model. So if you just look at the model analysis, these rotamers or sidechain conformations are quite good, and you don't feel this model should have problems. But these are actually out of the density, so they have to be corrected. So you may want to use programs that automatically eliminate outliers, but that should not be a good practice. If you find outliers, they should be quite useful, and you should go to that residue and check it against density include. Okay. And somehow I'm supposed to cover PDB redo part also, but I am not a PDB redo person. From here I'm using slides kindly shared by Robbie, who is also PDB redo. So you may have heard of PDB redo, but this is an automatic pipeline that automatically corrects or improves the model from X-ray or electron crystallography. So it tries to optimize the parameters of refinement programs, and also does some model rebuilding. And actually, there is a data bank of PDB redo that contains updated structures from the PDB. So if you go to the website pdbredo.eu, you can give PDB code to see possibly improved structures from PDB redo. And you can also use that web server to improve your model, and they can also actually be used from CCP4 Cloud. So today you can also try it. For this, you have to register at PDB redo website. But you can see this instruction on CCP4 Cloud as well. So the features of PDB redo include automatic treatment of NCS, the non-crystallographic symmetry and twinning. And it can also do paired refinement to find high resolution at all. And also it automatically selects the B-factor model, isotropic or anisotropic, and TLS. And can also do grid searches to optimize bulk solvent parameters. And also automatically select the weights for geometry or ADPs. The weights I just mentioned in the earlier slide. The model rebuilding feature of PDB-Redo includes peptide clipping. This is a very common mistake in the protein model building. So if a flip improves the density fit and Ramachandran plot, the program accepts that fit. And also does sidechain rebuilding and completion. So if the sidechain is missing, then PDB-Redo completes, it adds sidechain models. And if existing one is not related to its density very well, then it also fixes it. And these are also common mistakes, the histidine, asparagine, glutamine flip to be also done in PDB-Redo manner. So as a PDB-Redo website or from CCP4 Cloud, in case you give your structure to PDB-Redo, you can see these outputs. So as output, you get new model and new map coefficient, obviously, and also you get optimized parameters for RefMatchat program and extra restraints that can be used in the subsequent refinement. And of course, you can see various statistics, how much PDB-Redo improve your model. So, yeah, as a summary, structure refinement is an iterative process. The structure refinement programs like RefMat or SaberCat optimizes the model parameters against the observed data, the intensities or structure factor amplitudes, and then we do validate the model, and then inspect the model against the density in the real space using COOT, and we have to repeat this process. And the model parameters include atomic coordinates, and also displacement parameters, B-factors or ADPs, and sometimes occupancies. And maximum likelihood refinement is used, and stereochemical restraints are essential. And at lower resolutions, we need to use more prior knowledge, including secondary structures or conformational restraints from homologs or predicted structures. Conformational restraints in the form of distance, non-bonded distance, atomic distance restraints. So it is a structural biologist's responsibility to ensure the final most accurate model to be deposited and published. And I introduced RefMat 5 program that has been a primary refinement engine within System4, and it's being replaced by SaberCat. And lastly, I introduced PDB-Redo that implements various automated refinement algorithms. Can be also used from cloud. So finally, I just want to thank team members. So I had been working in Garib's group. So this is Garib, the author of RefMat. And in the same group, Faye is making A-struct program that will be used for the dictionary generation for ligands. And Paul, the author of COOT, and Rolf, who is the author of ProSmart and recently moved to STFC. And me, the author of SaberCat, and moved to the University of Tokyo 2 years ago. So, of course, I thank CCP4 for all this collaboration. So before moving to the tutorial part, do you have any questions? No. So now I have to use Charles project. This one?
Yeah.
This one?
The second
A second. Oh, this was the second. No, maybe not.
Yeah. This one's got the.
So I suppose you have the same stuff in your Tetris cloud. You also did model problems, right?
Can you make the font bigger? Can you make the font a bit bigger?
Oh, yeah.
Not too big.
This is good. Well, what should I do? Maybe maybe I'd rather use this red mark job to review the inputs and outputs. So I'd like to explain a bit more detail about input and output. So you have run this job. So 50 cycles of the refinement, and in this case, we didn't change all other parameters. For example, overall geometry weight. This is what I mentioned in this slide. This weight parameters that is applied to the data term. So smaller values means tighter restraints. But usually you should leave it default. So the default is old, and the starting value is also determined automatically from the resolution. So you should first try the default, and only when you find the restraint is too weak, too tight or too weak, then you have to change the weight value. The actual weight can be found in the log file at the end of ref mark, nearly end of the ref mark job. You see this number, this actual weight 5.6 to something is applied to the X-ray term. So you can start with this number. So if you want to make restraint tighter, then you may want to try smaller values, like 1 or something. But I believe most of the time the defaults should work well. And Van der Waals recursion weight, the default is 1, but if you give a larger number like 1.4 or 2, then it will reduce crashes. You may want to increase Van der Waals recursion weight at the final stage of the refinement. And the hydrogen atom, so it seems in CCP4 cloud while the default is all in command line. So anyway, if this is changed to yes, RefMark automatically generates hydrogen atoms at writing positions and use them throughout the refinement. And after the refinement, by default, it removes hydrogen atoms from the model. So actually, this is what we should also keep in mind. We do model building or refinement. Hydrogen atoms should be present in our protein, but in X-ray crystallography, it's very hard to see. So we usually don't explicitly model hydrogen atoms. But by considering hydrogen atoms, we can get more accurate model, hopefully. But this actually should be turned off at earlier stages when the model error is large. In that case, hydrogen atoms would just confuse the refinement. So this should be only turned on at the last final stages. So yeah, this is a good choice after the molecular replacement. I mean, we should set it no. And for other parameters, so we can change atomic p-factor parameterization. Default is isotropic, but at very high resolution, you may want to switch to this anisotropic ADP parameterization. But this can also be done at later stages, even if you have high resolution data. Just after molecular replacement, you don't want to use anisotropic ADP parameterization. This can be considered later stages. And we don't usually change solvent model type and explicit solvent mass parameters. This should be defaults. And it seems NCS restraint is on by default. This wouldn't do anything if you only have one protein chain in the asymmetric unit. But if you have multiple copies of the model in the asymmetric unit, then the program tries to keep the conformations in different chains similar to each other. The default is local NCS, which is a good choice because there may be some hinge motions across different copies. The local NCS restraints would allow such difference. And Jelly-body restraints, we change it to yes in this case because this is just after molecular replacement, but usually we don't use it after that. And there's an option for covalent metal link identification. So by default, program reads the link records into the model file, PDB file or MMC file for the special links like covalent link between the protein and the ligand. If such link are there, then link records should be in the model file. Otherwise, such connections, such bonds will be ignored in the program. But if you want the program to automatically find and use such special links, then you change this to yes. Then program try to find potential links. But in this case, you have to carefully check the log file or the model file after the refinement, because there may be some accidental links or could be used in the refinement. So in this case, you just have to choose what links should be used in the refinement. And this generic backbone hydrogen bond restraint is to use ProSmart program to set up secondary structure restraints. So it will be useful at low resolution refinement. And here is, I'm not talking about this today, but usually we don't need it. And output, yeah, about hydrogen atom and map sharpening, and we don't think we change this. And as an advanced option, obviously, if you are not working on X-ray data, you have to change this to neutron or electrons. So maybe that's it about input. But actually, if you when you set up a new refinement job, you would have seen you don't follow this. You don't have to follow this. I just want to show this option is a homologous model. So this is to set up a ProSmart type restraint using external structure like high resolution homologs or AlphaFold predicted models. You can give such models using this option to use such conformational restraints in the form of interatomic distance restraints. But today we are only dealing with very high resolution structures, so we don't do this. So let's go back to this our previous refinement job. So we already have seen this R factor and R field. And R factor is actually our work I explained in these quantities. So reflections used not used in the refinement are used in the refinement. So you see R3 is slightly higher than R work. I mean the gap is now about 2 points, so should be fine. And you can also check other quantities over the cycles. This is bond length RMSD from ideal values. So this is around, now this is around 0.01, so it should be okay. So for example, if this is larger than 0.02 or even more, then you want to tighten the restraint. But shouldn't happen. So, and this is about bond angles. Bond angles RMSD. It's a bit large here, but we may not have to worry about it in the early stages. And you can also check statistics, not about the past cycles, but maybe the last cycle R factor versus the resolutions. Looks quite well, quite good across all resolution range. And if you scroll down, you also see refinement summary and verdict analysis. It says something about the statistics after the refinement, and it suggests new parameters, the parameters for the subsequent refinement. We don't have to worry much about these things at early stages because the model will be improved anyway. But yeah, it also suggests increasing VDW recursion weights, which I just explained in the input tab. Okay, so I would like you to do some refinement procedure. For refinement procedure, I explained in my lecture. So you click, I think you previously clicked this good button, but click this again. And good is open. So please also read this message, because after rebuilding in Qt, we want to use that updated structures for the next refinement job. So we have to save the model using file save coordinates, and then when we close Qt, the saved model will be transferred to cloud server, and you can use it in the subsequent refinement job. So don't forget to save coordinates after you change something. By the way, anyone who hasn't used Qt before, so you know how to use Qt. At least most of you are quite familiar with Qt. Okay, then maybe we don't have to spend much time in this part, but I just want you to experience this Qt and cloud workflow. So now you can do whatever you want, but maybe I also have to do ligand fitting, right? So actually, when you look at the tutorial documentation, you are supposed to run a-struct job in cloud and use it in this Qt session, but I didn't do it, and I think it's better to explain the other cases. I mean, when the ligand is known, I mean, if the ligand dictionary is present in the monomer library, we can just use that definition. So in this example case, we can just load from file get monomer and put NUT and use this ligand coordinates. It's just loaded to the center, so it's overlapping with macromodule, but we don't have to worry about it because they are different objects or different molecules. So for now, I can just hide it. So yeah, somehow in the tutorial, we use Smiles string to generate ligand dictionary with this NUT residue name, but this should be only done, I think, when you are dealing with new ligands, because NUT is already defined and it has specific atom names. So if you regenerate a dictionary from Smiles, then you will end up with different atom names from the proper definition of NUT. So when the ligand is known, I mean, if ligand is present in the monomer library, then we just have to use it. Or we can, of course, we can also specify just NUT ligand code in the struct task. And for the new components, it's better to use reserved names like 00 or 01, not to overlap with existing ligands. So anyway, I'd like to follow the tutorial for ligand fitting. So I think from calculate other model tools. Then you can find the ligands button. Now you can select ligands because we just loaded this NUT. And we use this glue map for finding ligand position. So this first one is just okay, FWT, PHWT map. This is 2A4 minus FC map. And the program could mask the map using model, the protein part. So we use this. We don't have to change this. Anyway, the program masks map using this protein model. And actually, it should work with all the code. And if you check this flexible checkbox, it will be successful, but it will be too easy. I mean, nothing will have to be done. So I just intentionally uncheck this flexible, but you can also try this flexible option. And if I click find ligands, then the purple map just showed up. This is the map, density map, and it says it found one acceptable ligand. Okay, I have this dialog. It is ligand. So could successfully found the ligand position and placed the ligand. It's not fitted to the density very well because I didn't use a flexible option. If you use a flexible option, then it calculates several conformers and select the best fitted one. But in this case, I have to try to fit it to the density. It will be fun. I mean, if you are not quite familiar with COOT, then it will be a good practice to fit the ligand into this density. It may not be quite straightforward. So now I want you to play with COOT. You don't have to stick to this ligand fitting, but also use other COOT functions or just see around and find potential model errors and we correct them. Now I actually cheated and did flexible fitting. It ended up with very nice fit, but it still has some model error here, so we have to correct it manually. So when you finish model building for now, don't forget to merge this fitted ligand molecule into the protein molecule, because now you see this ligand model and protein models are different objects, different molecules. So yeah, maybe you are quite familiar with this type of thing, but you need to choose these large molecules from edit menu and select the fitted ligand object, molecule, into the protein part, the first object, first molecule. Okay, then you see these ligands with the same color scheme as protein. So now we want to save the model and refine it using RefMatChat again. To save coordinates, just select the first one, and we should just click Save button with default names. It's temporarily saved in your local, actually it's in X-Ray Cloud local. Then it's will be transferred to remote. So I think here Yeah, we can just hit exit if you save. And I don't need these models, so I just continue exit. Then I think now the saved model is being uploaded to the remote server. And good job is just done. So I think now you can just next job. Should this work? Okay. Refinement with refinement by buyer. Yeah. So now we don't want, probably we don't want many cycles with Jelly restraints. So we change number of cycles to 10. And in the restraint tab, we don't use Jelly restraints. So we change this to no. And then we start refinement. Here you can see it uses a model from Qt model building. So it finished so quickly, and our factors went down. I think it's doing some analysis, validation. I think we can quickly inspect the models and the map, model and the maps after the refinement using Agri mode. Yes. So yeah, you will notice the ligand is model. I mean, ligand is present in the structure, and we are no longer seeing F1 minus FC difference density in this ligand part because ligand is just model. So after that, you have to continue refinement. I mean, you click the button and inspect the model against the density, use various validation functions, and you may also want to place waters. That also can be done automatically, and save the model and come back to cloud and do refinement and repeat this process. So hopefully you got some ideas about refinement procedure using cloud and Qt. So maybe it's good time to move on.
Okay, we'll have tea and coffee outside. Tea and coffee, then Ronan will do